Hello and welcome to another video in a series dedicated to engineering thermodynamics. Today I'm going to talk about the first law analysis of control volumes. So in this video I'm going to talk about mass flow and conservation of mass. Then I'm going to talk about the concept of flow work and the amount of energy a moving fluid carries. Then I'm going to talk about the first law analysis of the control volumes. And finally, I'm going to give some examples of both steady state flows and unsteady flows. Okay, so let's start with the concept of mass flow rate and the conservation of mass. Now, mass flow rate, we discussed it before in another video, can be written as delta m dot is equal to the density of the fluid, velocity of the fluid, cross-section area of the element of the fluid. So if this is the pipe and fluid is flowing through it, fluid inside has a velocity profile like this, then in order to find the actual mass flow rate, you have to make an integral of delta m dot, which will give you integral over the cross-section area of density, fluid velocity, the cross-section area. Okay, now velocity usually has a relation with the area element, and then we can make this integral, but we want to make our lives easier in thermo. We don't really want to go too deep into the math behind these equations because that's a topic for fluid mechanics course, not thermodynamics. So we're gonna simplify this equation. So I'm going to first define a new velocity that will get rid of this profile. Now I'm gonna define an average velocity in the form of 1 over cross-section area integral of velocity dA. Okay, now this represents a profile like this. Instead of having a dependency on the area, we are dealing with a uniform velocity profile. So the blue profile inside the pipe is the average velocity, while the black one is the actual velocity profile. Now, by choosing to work with the average velocity, we are simplifying the equation in the form that this integral reduced to m dot is rho. The only condition for this equation is that rho, or density, is not a function of cross-section area, which is pretty much given in most of the problems and cases that we deal with. Density of the fluid is not a function of the cross-section area or the location inside the pipe. So this is the mass flow rate. We know that we have another quantity. We show it with V, capital V dot, and it is V average cross-section area. We call this one volumetric flow rate. Now, mass flow rate has the unit of kilograms per second, while the volumetric flow rate has the unit of meters cubed per second. Okay, we can start talking about conservation of mass. Now, mass in nature, just like energy, is a conserved property, and it cannot be created or destroyed during a process. However, we are very familiar with the famous Einstein equation that relates energy to mass. Actually, it relates both energy and mass together in the form of energy is mass times the speed of light squared. Now, this equation means that when the energy level of a system changes, some of its mass converts into the energy, or some of the energy converts back into the mass. Now, for nearly 100% of engineering applications, the amount of mass transferred during the process into or out of the energy form is negligible. I mean, it cannot be even measured with the most accurate devices. So we can neglect this equation for the purpose of thermodynamics. Now, with that out of the way, the conservation of mass states that whatever mass enters the system minus whatever mass goes out of the system is equal to the change of the mass of the system. In the rate form, we get mass flow rate coming in minus mass flow rate going out is equal to rate of change of mass of the system. The top equation has a unit of kilograms. The bottom equation has kilograms per second. So we have two major categories going forward. We have steady flows and unsteady flows. Now, what does this mean? What does this mean? What does a steady and unsteady mean? So for steady, imagine a very complex system. We have a pump here. Water is pumped to boiler, and then steam is redirected to a turbine, and then from there the leftover goes into some sort of a heat exchanger, and then the water is redirected back into the pump, and this cycle continues. Let's go check some water properties at different states. Let's say the exit of the pump has the pressure 1, the exit of the boiler has pressure 2 and temperature 2. Now, after the turbine, it has pressure 3 and temperature 3. And after the heat exchanger, the same, P4 and T4, and this was P1 and T1. Although these pressures and temperatures are different across the system, across different locations throughout the system, at any given time, if I come back and measure any of these at the same exact location, I will read more or less the same number. For example, if I read pressure and temperature 3 at this location, and then come back 2 hours later, and I redo the measurements, I will still read P3 and T3. 1 day later, if I come back and read, it's still P3 and T3, right? The same goes for any of the other measurements. This will be P4 and T4. This one P1 and T1, P2 and T2. Not only like this in a cycle, but even on a smaller scale. Let's assume a diffuser. So we have a pipe, and then it enters a diffuser. So we have a flow coming in, and then we have a flow going out. So the velocity coming in is velocity 1, and the velocity exiting the diffuser will be velocity 2. So velocity 1 and velocity 2 are different, okay? So there is a dependency on location. If you are measuring your velocity here, it will be different than if you measure your velocity over there. So there is a spatial gradient, there is a spatial difference. But no matter what time you come back and measure at this same position, you will still read velocity 2. So the changes of velocity are dependent on the location inside your system, but they are independent of time. So a steady flow is when the parameters do not change with time. Remember, they can have differentials and spatial changes, but they cannot change with time. Now, unsteady flow is the opposite. Parameters can change with time. Okay, so if parameters do not change with time, then d dt of every parameter or every variable is going to be 0, right? So if we write back our conservation of mass equation, we get that m dot coming in minus m dot going out is 0. Now, m dot coming in is velocity entering, cross-section area, density, all three at the entrance. Mass dot going out is velocity going out, cross-section area of the exit, the density of our fluid at the exit, right? So I can play with this equation and get velocity I, entrance, cross-section area I, density I is equal to velocity out, cross-section area out, density out. So in a special case that we are dealing with steady flows, the conservation of mass reduces to this equation. However, we can simplify this even more with some certain conditionings. Now, if the density of our fluid remains constant, we call the fluid incompressible, and then we can cross the densities from both sides of the equation and get velocity entering times cross-section and area of the entrance is equal to velocity of the exit, cross-section of the exit. Now, because this is thermodynamics, we usually work with the specific volume. So remember that density is 1 over specific volume. So constant density means constant specific volume. Now, if we are dealing with steady state flow and we are having an incompressible fluid, usually a compressed liquid like water, then the conservation of mass reduces to this equation. Let's go to the next topic, flow work and the energy carried by a flowing fluid. Okay, so let's assume this pipe like this, and then we have our fluid element here with the pressure of P and a specific volume V and a mass M. The fluid just upstream of this blue element is pushing our blue element downstream of the pipe. The mass of the fluid upstream is applying a force F on our fluid element and is pushing it down. So let's say because of this push, because of this red force, the blue element has moved here. Right? It has moved down for a distance of d. So the amount of work that the upstream mass of the fluid is doing on the blue element is the force times the distance that is moved. I know that the force is actually pressure times the cross-section area of the pipe times d. Now cross-section area of the pipe times d gives us the volume that this element has moved. So we get pressure, volume. So the upstream flow has done a work on our fluid element. That work is pressure times volume in kilojoules. We can write it per unit mass in the form of small letter w is P specific volume in kilojoules per kilogram. Now this term is called the flow work. Okay, now the total energy of any system, we know in per unit mass is E is equal to kinetic energy plus potential energy plus the internal energy, right? Which is velocity squared over 2 plus G times Z plus internal energy, right? Now for a flowing fluid, we have the additional term associated with the flow work. So the total energy of a flowing fluid element is going to be kinetic energy plus potential energy plus its internal energy plus the flow work. We show this new energy with the Greek letter theta. The unit is in kilojoules per kilogram still. Now, if we take a closer look at this equation, it's actually very interesting. The terms kinetic energy, potential energy, and P times the specific volume, we saw these three together once before in the definition of mechanical energy. Now remember that a pressurized fluid had another sort of energy separated from kinetic and potentials, and we showed that with the term PV, and we called the summation of kinetic, potential, and PV the mechanic energy. So in other words, we can say theta is the mechanical energy plus internal energy. That's why theta is the total energy carried by a moving fluid. So let's take a closer look at theta. Theta is kinetic energy, velocity squared over 2, plus potential energy, Gz, plus internal energy, U, plus PV. Now, by definition, U plus PV is enthalpy. So, theta is velocity squared over 2 plus Gz plus enthalpy. So the total energy carried by a moving fluid in or out of our control volume is shown by the Greek letter theta, and it's the summation of kinetic energy plus the potential energy plus the enthalpy of the fluid. Now the total energy transported by mass is E, or the total energy transferred by mass. I'm gonna write the mass on the subscript here, is m theta, which is mass times enthalpy plus kinetic energy plus potential energy. And in the rate form, the rate of energy carried by mass is m dot theta, is m dot enthalpy plus kinetic energy plus potential energy. The top equation is in kilojoules, and the second one is in kilowatts. Okay, we can start talking about the first law analysis of control volumes. So from a previous video, we know that the first law of thermodynamics for a control volume can be written as U net minus W net, all the energy is coming in with mass, minus all the energy going out with mass, is equal to the change of total energy of the control volume. Or in the rate form, we will have Q dot net minus W dot net plus all the mass flows coming in minus all the mass flows going out is the rate of change of energy of our control volume. Now the first law equation all by itself usually is not enough. We need an additional equation to address the issue of the mass flow rates. That's where the conservation of mass comes in. All masses coming in minus all masses going out is equal to the change of mass of our control volume. And in the rate form, all the mass flows coming in minus all the mass flows going out is equal to rate of change of mass of our control volume or system with respect to time. Now, we need to couple these equations together in order to solve nearly all of the problems involving control volumes. We need to couple these two equations together and these two equations together. So basically rate forms together, non-rate forms together. Okay, so let's start with steady flows. So steady flow basically means that there is no change with respect to time. So ddt of any parameter or variable in our problem is 0. This means that our equations reduce into Q dot net minus W dot net plus all the mass flow coming in minus all the mass flows going out is equal to 0. Also, all the mass flows coming in minus all the mass flows going out is 0. So from the bottom equation, you get that this is true. And then we can plug in what we have into the top equation and get Q.net minus W.net is equal to all the mass flows, dropping the subscript because both of them are the same, times theta out minus theta in. Now I'm going to expand this equation. You get Q.net minus W.net is equal to sigma m dot times HO minus HI plus velocity O squared minus velocity I squared over 2 plus G Z out minus Z I. So this is the first law of thermodynamics for steady flow control volume. The unit for this equation is kilowatts. Now the previous equation for single streams, meaning that our control volume has only one entrance and one exit. So for a single stream scenario, I can reduce the previous equation even further to Q.net minus W.net is equal to m dot HO minus HI velocity O squared minus velocity I squared over 2 plus G ZO minus ZI. We have a per unit mass equation as well. Divide everything by m dot, you get Qnet minus Wnet is equal to HO minus HI velocity squared O minus velocity squared I over 2 plus G ZO minus Z. Now, if potential energy and kinetic energy can be neglected, then I get Q.net minus W.net is equal to mass flow HO minus HI. Now, this is an important equation because in most problems that we deal with in thermodynamics, we can neglect both potential and kinetic energies. We can have the per unit mass equation as well. Qnet minus Wnet will be HO minus HI. Further down the assumption line, if we are dealing with an ideal gas for our fluids, then HO minus HI is actually Cp, temperature of the exit minus the temperature at the inlet. Okay, so some flow examples. So the first example is pipe flows. We deal with scenarios involving pipes a lot, and if the pipe is like this and this is our control volume, then we have a fluid coming in, a fluid going out, and pipes usually have a uniform cross-section area throughout, so the area at both ends are the same. Now, conservation of mass says that velocity, so this is the entrance and this is the exit, so velocity I, rho I, cross-section area is velocity out, rho out, cross-section area. Again, because we're dealing with a pipe, usually cross-section area is uniform across the pipe. We can cancel the cross-section areas and say velocity I, rho I is velocity out, rho out. Further, if we are dealing with an incompressible flow, we get that the densities are the same, so we can cross them as well. And we get that the velocity at the entrance is equal to the velocity at the exit. So the change of kinetic energy is non-existent. Now, a pipe flow is usually on the same elevation throughout, so the change of potential energy is also negligible. So all that remains is Q.net minus W.net is equal to mass flow times H exit minus H entrance. So unless stated otherwise, this is the equation to go to for a pipe flow. So another example immediately following the pipe flow is the flow in nozzles and diffusers. Now, a nozzle is a piece of piping equipment that usually connects two pipes with different cross-section areas together, going from the bigger pipe to the smaller pipe. So this is the nozzle in the middle. Now, if we take the nozzle as our control volume, then we have the velocity coming in at the left boundary and velocity going out on the right boundary. Now, again, if you write down the conservation of mass, you end up, and assuming that we are dealing with an incompressible flow, you end up with, so we're dealing with an incompressible flow. We end up with velocity entrance cross-section entrance is equal to velocity exit cross-section of the exit. Now, please pay attention that a nozzle, the exit, the cross-section at the exit is smaller than the cross-section of the entrance. So the velocity at the exit, which is the ratio of cross-section of the entrance to the cross-section of the exit times the velocity at the entrance, will be significantly larger than the velocity at the entrance. So in a nozzle, our fluid gains velocity. Now, usually in a nozzle, the pressure of the flow goes down while the velocity goes up. Okay, so it is a device that converts the flow work into kinetic energy. Okay, now a diffuser is the opposite of this. Now, a diffuser is a device used in piping systems to connect two pieces of pipes, again with different sizes. This time the flow is entering through the smaller area and exiting through the larger area. So for a diffuser, if this is the entrance and this is the exit, for the diffuser, cross-section area of the entrance is greatly smaller than the cross-section of the exit, and so the velocity at the exit is way smaller than the velocity at the entrance. So again, a diffuser is a piece of device that increases the pressure at the cost of velocity. So it actually turns kinetic energy into flow work. Another example will be the turbines, compressors, and pumps. Now, a turbine is a device that creates shaft work or power at the expense of the enthalpy of the fluid. So it converts enthalpy of the fluid into power output. We usually show turbine like this, where this is the entrance, flow enters from the left-hand side and exits through the right-hand side. So the flow, usually in the problems, in the schematics of the problems, the flow enters from the narrow side and exits from the broad side. The compressor is the opposite. We usually show it like this. The flow enters the broad side and exits from the narrow side. Now, a compressor actually consumes work and increases the enthalpy of the fluid. Okay? A pump is just like a compressor, but deals with liquids only, right? And it consumes work to increase the enthalpy of the fluid. Now, for all three, we can neglect the potential energy and the kinetic energy unless stated otherwise. So for all three of these components, we end up with the equation in the form of Q net minus W dot net is equal to the mass flow times HO minus HI. Now the final example is a throttling valve. Now any kind of flow restricting device that causes a significant pressure drop without including work is a throttling device. Now examples of throttling devices are a throttling valve, which blocks the flow inside a pipe, leaves a small opening for the flow to move through. Another example is a capillary tube, which is mostly used in refrigeration and air conditioning cycles. As you can see, there is a significant drop in area inside the piping system, which causes the pressure of the flow to drop. Because they are very small, there is no time during the process to do any heat transfer. So usually Q dot is 0 for a throttling valve. Also, by definition, they do not include any work. So there is no work involved as well. Now, in nearly all the cases, we can neglect potential and kinetic energies as well. So what we get is that m dot h of exit minus h of entrance is equal to 0, or h of exit is equal to h of entrance. So a throttling valve is a very curious device. The enthalpy throughout the process inside the throttling valve remains constant, so it's an enthalpy constant device. We sometimes call the enthalpy constant process an isenthalpic process. So remember the definition of enthalpy. Enthalpy was the flow work plus the internal energy, right? Now, during a throttling valve process, flow work at the entrance plus the internal energy at the entrance is equal to the flow work at the exit plus the internal energy at the exit. Now, throttling device causes a pressure drop. So, pressure entrance is way larger than the pressure at the exit. Combining this equation and this inequality together, we can conclude that the internal energy at the exit is way larger than the internal energy at the entrance. So a throttling valve is a device that converts flow work into internal energy. Just like a nozzle was a device that converted flow work into kinetic energy, throttling valve converts flow work into internal energy. Okay, let's talk about the unsteady flows. We need to combine the first law of thermodynamics and the conservation of mass. Mass coming in minus mass going out is equal to the change of mass of our control volume, which can be written as mass coming in minus mass going out is equal to m2 minus m1 of the control volume. And then we have the first law stating that Q net minus W net plus all the energy coming in minus all the energy going out is equal to change of energy of our control volume, which is m2 E2 minus m1 E1. Now, although the problem is unsteady and the control volume, everything inside control volume is time dependent, we need to make some assumptions. The most important one is that any interaction at the boundaries of the control volume, at the inlets and exits, are uniform and independent of time. Now, an example for an unsteady flow is a bathtub. So this is your bathtub, and this here is the drain, and we have the shower. So water is coming into the bathtub and some water is going out of the drain. So if this is my control volume, the bathtub is my control volume, this is the exit going to the drain, a mass flow rate is going out, mass flow out, and then the water from the shower is entering my control volume, bathtub I, and you know from experience that the water level inside the bathtub gradually starts to increase, starts to go up. Now, as the time goes on, you are adding mass from the top, you're draining some mass from the bottom, and the overall mass of your control volume is increasing. So this is an example of an unsteady flow. Now, if you want to analyze your bathtub thermodynamically, you need to use both of these equations, conservation of mass and conservation of energy. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again and see you in another video.